You're listening to a podcast from 702 and Cape Talk.
702 and Cape Talk.
The Naked Scientist.
Chris, good morning.
Hello.
Lovely to be with you. Thank you for joining us. And our lines are open for you, by the way. Anything that you want to ask the Naked Scientist, Chris Smith, give us a call on 021 446 0567 011 883 0702. How life began. Are we closer to answering that question, Chris?
Very, very interesting paper out this week, Reedy, in the journal PNAS. Group of researchers at the Czech Republic Academy of Science, this is a guy called Martin Ferris and his colleagues, and they have recreated the environment of the Earth about 4 billion years ago using nothing more than a laser and a Petri dish. And what they were trying to understand is where the building blocks of life came from. We know that every form of life on Earth that we know of uses a form of inherited material, either DNA or its chemical relative RNA, or both. And the chemical building blocks of this molecule, DNA or RNA, have the amazing ability to copy themselves. They're self-replicating. They've effectively built little machines out of themselves that can copy themselves. So one theory of where life got started, or how it got started, is that sometime back in history, around about 4 billion years ago, which is when we think it happened, these molecules came into existence and they began to copy themselves and ultimately evolved to enshroud themselves with a fatty membrane. You could call that a cell. And then ultimately, 4 billion years or so of evolution later, here we are. But where did those molecules come from in the first place? The tantalizing thing is that the arising of life on Earth coincides with a phase called the Late Heavy Bombardment. The planet was being battered relentlessly for 150 million years by these massive objects raining in from space. This is probably because Jupiter wiggled a bit in its orbit around that time and dislodged asteroids and comets and put them on an earthbound course. But as these objects, and in fact there was 1 billion tons of material raining in on Earth every year for 150 million years, when these things came in at a speed of about 20 kilometres per second, slamming into the Earth's surface, they would have created very, very powerful and energetic reactions. That's what this group have recreated with an iodine laser in their laboratory. So they took some samples of a solution of formamide, which is a very simple biochemical, very, very common, relatively speaking, on the early Earth. They zapped it in the presence of some clay with this laser, with pulses that were just 1/3 of a billionth of a second long, and this heated the material to more than 4,000 degrees, which would have been equivalent to a sort of temperature that the Earth's surface would have got to in places where it was being hit by these comets and asteroids. It also creates a very big shock wave, because if you hit something with a big burst of laser energy and make it expand because it gets so hot so quickly, the shock wave then ripples through the material in the same way you would get a shock wave if a big impactor came in from space. Amazingly, having done this experiment, then if you look in the solution of what you've made, you've rearranged all the atoms in this formamide and made other chemical reactions happen, and there are the 4 chemical building blocks of the RNA message, which is in all of our cells, just spontaneously occurring. So this shows that you can make very complicated, very important fundamental building blocks of life from what would amount to an asteroid impact, and that's why they're suggesting that life could have got started at the time when this late heavy bombardment was happening about 4 billion years ago.
And then, Chris, I couldn't resist this. I made a mental note to ask you, so here we go. On your Twitter account, there was a question about opera singing, that it is as much a science as an art. What's that about?
Well, what we do on The Naked Scientist is that once a month we decide to have a little bit of a party, relatively speaking. So instead of just sitting in a radio studio to do the programme, we go to a science centre and we set up a whole bunch of microphones and we invite the audience to come in and we invite some scientists to come in and we have a sort of open forum. But we try to theme the scientists and link them all together. And we did the last programme on the science of sound. So having explored what sounds are and then explored how your brain picks up sounds using your ears, so how your ears work, how hearing aids work, and also how we can make better hearing aids, we then looked at how you can steal from an owl. Effectively, owls fly really quietly. How do they do it? Well, there's a mathematical trick they use, and we talked to a scientist who's trying to do the same thing with aeroplane wings in order to make an aeroplane fly much more quietly. And the final person on the billing was a lady called Nicole Francis Gaultier. And she started off as an opera singer, then became a scientist and spent a number of years developing drugs that will affect the nervous system. And then she realised that her first love really was singing. So she resigned her job as a scientist and she's gone back to singing. And now she sings professionally, operatically all the time. But she uses her science to inform her opera singing. And she said, I probably do more science in terms of my thought processes now I'm a singer again than I did when I was a scientist, because it's all about, and she explains about the way in which you do breath control, muscle tone and voice control and shaping your mouth and projecting and things. And it was really interesting because when we sat these scientists down behind the microphones, as you know, when you sit people in the studio behind a microphone, some people really, really are almost scared of a microphone, and they're very, very quiet, and they don't sort of project their voice. We had to turn the gain on her down as low as it would go on the mixing desk, and then some, because just her natural speaking voice, she's naturally learned to use science to project her voice and make it very loud without actually trying, and that's all to do with physics.
Incredible. Let's go to Les in Mondio. Hi there, Les. You want to ask a question about my favorite food, or one of my favorite foods?
Yeah, Chris?
Good morning.
Good morning. We know reptiles and the poor old platypus lay eggs, but I'm interested in how birds produce their eggs. They all eat different types of food, but they produce a similar shell.
Okay, how are eggs produced? Sorry, Les, I'm going to have to let you go. Your radio
What came
is on
first,
in
the chicken or the egg? Well, the answer is egg. The answer is, Les, that they have an oviduct, just like we do, and the egg forms at the top of that oviduct, and it slowly meanders its way down the oviduct, and there is a membrane around the outside of the egg into which cells that can deposit calcium, almost in the same way that you have cells that deposit bone, are resident, and calcium is taken out of the bird's bloodstream, and that calcium comes out of the bird's bloodstream from the bird's bones, and it's deposited into the lining around the egg by these special calcium depositing cells. And once the egg finishes its journey from the top end of the oviduct out to the ovipositor at the bottom end and pops out into the world, it has completed that journey of getting completely calcified, and it's a calcium carbonate coat round the egg. And the interesting thing, you brought up reptiles. The interesting thing there is one of the pieces of evidence that birds are the survivors or the descendants of dinosaurs. If you look at how birds and dinosaurs handle calcium in their body, they have special reserves in their bones of easily accessible calcium, which comes and goes during the breeding season. In other words, when birds are breeding and laying lots of eggs, their calcium demand goes rocketing up, so they borrow from their bones, and when they're not laying eggs, they put the calcium back again. And you can see this reflected both in modern bird skeletons but also in fossils of how these calcium, almost like tree rings, grow and shrink in accordance with the breeding season.
Let's go to Matt in Kailami. Hi.
Hi, good morning. My question is, when candles are in candlesticks, what happens to the wax when the candle melts and there's no wax left? Does the wax evaporate, or... I'll listen on the radio. Thanks.
Thank you.
Hello, Matt. So how does a candle work? Well, a candle works because the wax is the fuel. The wick soaks up the fuel and introduces it to the flame where the temperature is really high. Where the temperature is really high, this fuel, which is hydrocarbons, it's chains of carbon atoms linked together. There's probably about 15 to 20 carbon atoms in a long chain in candle wax. This absorbs energy from the flame, turns into a vapour now. The vapour mixes with oxygen from the air, which is being drawn in at the base of the flame. The oxygen reacts with the hydrocarbon, producing carbon dioxide and water, and a lot of heat. The air expands and starts to rise because it's less dense, pulling in more fresh air at the bottom of the flame, but some of the heat is transmitted onto the candle base where there's more solid wax, melting more wax, which goes back up the wick, and the process continues. So the candle wax is the fuel, and as the candle burns, it burns off the fuel, and therefore it shrinks and disappears. And what you've done is to turn the solid wax in a solid hydrocarbon form into gases in the air.
Let's take a break, and then we'll be back with more of your questions. Itumeleng and George, I see you. We'll be chatting to you in a moment.
702 and Cape Talk.
The Naked Scientist.
And Chris is here to answer your questions. You know, those vexing questions that you sometimes lie awake at night and you think, how does this work? Why does this happen? Well, we do our best to provide that platform for you. Call us on 021 446 0567 011 883 0702. Let's go to George in Belleville. Good morning, George.
Morning, Chris.
Yes.
My question is just, why do we, when we're extremely happy or extremely sad, we shed tears?
Why do human beings cry when the emotions are so different? Happiness and sadness. Chris?
Hi, George. Yeah, I mean, it doesn't happen so often to me, but it has happened, so I can experience it. I can say I've experienced it. I think when my daughter was born, I felt a little bit teary. When I got married, I think I felt a little bit teary. But also when we're unhappy, we get a bit teary. Why do we do it? Well, humans are really visual-dominated animals. More than a third of your brain is given over to processing what comes in through your eyes. Vision is a really neurologically hungry sense. And in other words, we put huge prominence on vision. So we have evolved as a social species to have signals that we can send from one to the other, which will plug into our visual system and tell us, I have a problem with something, or I have something to be excited about. And crying is a very visual signal, and it therefore encourages other people to come and help you or to share in your happiness, both of which involve stronger social bonds. And for that reason, it's a good way of getting people to become closer to you. And if you have lots of people who are closer to you, you're more likely to be successful as a species if you're a social species. Why use crying, and why use the same signal for both things? Well, crying is often not done in isolation. People often cry and look sad, or they cry and look happy. So in other words, it's a way of emphasising the manifestation of emotion. People can look a bit unhappy, but not be as unhappy as if they're crying. If you cry, then it says, whatever I'm feeling, and showing you I'm feeling, I'm adding icing on the cake to make it really, really clear how strong my feelings are.
Thank you. And is it Brian in Milnerton? Hi.
Hi. I'd like to ask the naked scientist the following. That, he mentioned about how evolution had taken place. That had evolved over millions of years. And I'm wondering how that ties in with the principle of entropy, or the theory of entropy, where things slowly devolve into chaos. But how did things become more complex when we live in a world today with entropy, where things become more chaotic?
You're absolutely right. And in fact, Boltzmann was the man who invented entropy. And I think this is more than 100 years ago now. I think it was in Austria. I think it was an Austrian scientist. But the theory of entropy is that everything in the universe is moving towards disorder. And in other words, you can explain why things happen because they go from a relative state of order to a state of greater disorder. But that's not to say that everything exclusively has to become more disordered, because as long as there's a payback, then you can have something which is more ordered if it also gives rise to something that's more disordered. A bit like Parliament. In other words, if I make a reaction happen and I have a chemical which is a liquid and another chemical that's a liquid, and I react them together, let's say they make a solid. Now that's more ordered because it's a crystalline structure and highly organised, and you think, well, that must be a negative entropy. It's not going in the right direction. But let's say the reaction also gives out a lot of heat when it forms that solid. The heat then also goes off into the environment, and that has a very big positive entropy. So the positive outweighs the negative, and so it still happens. Now, in terms of humans, yes, there is an organisation from disorder when you're assembling biomolecules and bringing them together and making life, but at the end of the day, the ultimate entropy change is one of more disorder, because there's energy coming into the system and ultimately becoming more spread out, but it goes via a more organised state, if you can call us that, in the meantime.
Let's go to Itumeleng in Benoni. Good morning to you, Itu.
Hi, Chris and Reddy. It's a pleasure to be on your show.
Thank you.
Chris, there are two institutions. One is CERN in Europe, and the other one is the Opera Research in Italy. And both of them differ on one fundamental principle of that neutrinos travel faster than the speed of light. And that is the point of view from Italy. And the point of view from CERN is that they have found no shred of evidence in their experiments to prove that neutrinos travel faster than the speed of light. I just wanted to hear your opinions on that.
Good morning. Well, there was a lot of fanfare. You probably remember a year or so ago there was a number of headlines being produced about saying, have scientists found particles travelling faster than light? Subsequent experiments show that this was not the case. The reason that it occurred was because of some mathematical difficulties. In fact, there's no evidence that anything travels faster than light. Neutrinos are very tiny particles which you can detect in things like the sun, and they're whizzing through the Earth all the time. They're very poorly interacting forms of matter. They're very, very tiny, very, very light, and that's why they're called neutrino, because the eno on the end denotes very, very tiny. And the evidence is that they too, despite being very, very tiny, are bound by the same rules that bind other matter, and they can't break the cosmic speed limit that Einstein set of the speed of light. So it is not correct to say that neutrinos break the light speed limit, because apparently they don't.
There we go, Itumeleng. Thank you very much for the question. And is it Lindsay in Newlands? Hi.
Hi, Chris. Hi, Reedy. Thanks for a lovely show.
Thank you.
My understanding is that energy doesn't get destroyed. There's as much energy in the world now as there was at the start, and there always will be. But if you move a weight, say a box, from A to B, you use up energy in that movement.
Mm-hmm.
All right, you might produce a bit of heat, but there's some energy that's used up. It's finished. It's been used in making that thing move. So how does this work?
You're absolutely correct that there is the same amount of energy in the system all the time. At any one moment in time. The Earth is gaining energy all the time, of course, because it's being hit by energy from the sun. It's also losing a bit of energy out into space, but it is slowly warming up a little bit, so the Earth's overall energy is slowly increasing.
Mm-hmm.
But if you take any system, let's take your box example, the box at rest isn't doing anything, it's just sitting on the table. But that doesn't mean it's got no energy in it, because if the table is raised off the ground, the box is experiencing a force owing to gravity pulling it towards the ground. The box can therefore be thought of as having gravitational potential energy. If I nudge the box and knock it off the table, the gravitational potential energy is converted because of gravitational acceleration. The box falls towards the ground. That gravitational potential energy is converted to kinetic energy, movement. But as the box goes through the air, it's bashing into air molecules, pushing them out of the way, and through the effects of friction is therefore generating some heat. Now we've got heat energy, which is vibrations in atoms in the air, and the box has got a bit less energy. It then slams into the floor, and there's a banging noise. That's some sound energy, and a bit more heat because it compressed the floor, and now it's lost its gravitational potential energy, converted it via kinetic energy into kinetic energy of molecules in the room and sound energy, but now it's sitting on the ground and has less energy. So the whole thing can be explained in terms of conversion of energy, but overall the energy is relatively the same.
Thank you so much, Lindsay. Fascinating question. And speaking of losing energy, burning energy, here's an SMS. Please ask the Naked Scientist, why is it so hard to lose stomach fat?
Well, the reason is that fat is so energy dense. We've evolved to use fat as our energy storage vehicle because you can pack enormous amounts of energy into the chemical bonds that make up fat. There are between 16 and 20 carbon atoms in chains in body fat. And every single one of those bonds stores a huge amount of energy. And when the body metabolizes or breaks down fat, what it's doing is taking little 2-carbon chunks. So you snip off 2 carbons from your fat, you react it with oxygen, and you make CO2. Making those new bonds releases a lot more energy, and that powers your cells. So the body has evolved to use fat because it can pack a huge amount of energy into the fat, but that means that you've got a very big energy store there. So to get rid of it takes a really long time to burn it off. And there's also some evidence that different parts of the body store fat preferentially in some people. In ladies, they tend to store fat around the breasts and also on your backside and hips. This is thought to be a healthier distribution of fat because it coincides with lower risk of things like high blood pressure, stroke and heart attack. And that's probably because it's a good way of storing energy for, say, baby rearing. Whereas in men, there's often a predilection to store fat around the midriff in the stomach, and you make an apple shape. This is coincident with a higher risk of stroke and high blood pressure and heart attack and high cholesterol levels. And it would appear that storing the blood around the abdominal viscera, which is where it's all stored, around your organs inside your abdomen, this is very bad for your health. Now, in terms of getting rid of fat, the best thing to do is to increase your metabolic rate. That means taking exercise, because the more exercise you take, the more lean tissue you have, muscles, and the more muscle you've got, the more lean tissue, your metabolic rate must be higher, and therefore you have the more capacity to burn off the fat. But there's no point in increasing your metabolic rate if you don't also cut down your metabolic intake and eat less, because then there will be a net conversion of stored energy into carbon dioxide and activity leaving your body, and therefore you will lose weight.
There we go. Let's go to Lucas. Lucas in Midrand. Good morning.
Good morning, Rudy. How are you doing?
Good. Your question?
I'm a bit nervous.
Oh,
Rudy.
okay. Don't worry. Take
Yes.
a deep breath. Take a deep breath. I don't bite, I promise you. And it's so much fun when you call me. I love it. So go for it.
No problem. I
Yeah.
just want to ask Chris, I've got 2-month-old baby. So he forever smiling while he's sleeping. So I'm wondering, does he see anything or does he smile anything? Because when I ask the elders, they always say, no, he's chatting with ancestors. Don't worry, he's fine.
Oh,
Is that
okay.
true?
So you wonder why your child is always happy and smiling. Well, maybe it's because he's got a nice dad or mom. I don't know, Chris. How do we explain baby's perception of happiness?
Well, babies dream, of course, and when they go to sleep, babies spend a huge amount of their time asleep because their body has to do an enormous amount of growing. And as a result, the brain is doing an enormous amount of growing as well. So when babies are asleep, they're still dreaming and the brain is still active. And there are still the capacity for messages to reach parts of the body. You don't move as much when you sleep, but you do move a little bit. And I suspect he's having some sweet dreams.
Just enjoy it, Lucas. Enjoy it. Because one day they scream, they cry, you don't know what's wrong, but a happy, smiling baby.
But what about the children? That's just the adults, isn't it?
Okay, do we have some time for this one? Okay, let's just try. If not, we'll bank it for next week. Sando, hi.
Yes. Good morning.
Yes, good morning.
I would like to find out if you drink water, do you get any oxygen into your system, or what's happened to the hydrogen and the oxygen, or you just passing through and no, you don't gain anything?
Okay, so what happens to the chemical composition of water when you actually drink it, Chris?
There is a little bit of oxygen dissolved in water, and we know that because fish and other aquatic species that have gills, for example, are extracting dissolved oxygen from water and putting it into their bloodstream. But this is inconsequential for a human who get gas into their bloodstream through the lungs. When you drink water, water is the molecule H2O, 2 hydrogen atoms glued to 1 oxygen atom. This goes into your stomach and then into your intestines, and it is absorbed into your bloodstream, and your body tightly regulates how much water is in the bloodstream through your kidneys. You have receptors that can detect what your blood pressure is, and the body interprets how much water there is in the body by what your blood pressure is. And if the blood pressure goes up a bit high, the body assumes that you're being overfilled. It's like cramming too much liquid into a tube. So the kidney filters off some water. You lose volume as urine, and this puts your blood pressure down. Conversely, if the blood pressure starts to fall, you do feel more thirsty because your body reasons that if the blood pressure has fallen, you must be oozing water out of sweat or urine or other body fluids. Therefore, you need to refill your blood vessels a bit more, so it triggers a sensation of thirst, and you drink a bit more to compensate, and this keeps the status quo.
Chris, have a lovely weekend. Bye-bye.
And you, thank you very much. Bye, everybody.
And then we will podcast this conversation with Chris. Thank you for participating.